Hey guys, Y13A here. Today I'm excited to show you guys the YX-10 Astra, the latest design in the YX series. This project has been in the making for a very long time, and I'm excited to finally show you guys what I've been up to. This design in many ways was informed by past experience and also contains new features that lay the foundation for future designs. Let's start by walking through the fuselage design. The fuselage started with a base plan form that was purposefully designed and drawn out. For example, here at the trailing edge of the canard, you can see a notch, and that notch serves to provide a transition from the mid-fuselage to the nose. And similarly, there is another notch here at the main wing root that transitions from the mid-fuselage to the wing. And at the end here, we have a taper from the fuselage, from the wings to the center line. And back here we have a fairing, and I'll discuss what that's about later. So it's very purposeful and kind of refined geometry, and this was due to a new kind of methodology in design. Basically, I started from the outside and I worked in towards the center. This resulted in this very clean design with a very smooth outer mold line. It has also defined contours, and so if you look from the front, you'll see a triangular cross-section. The all-new Control Surface Actuation Mechanism, or CSAM for short, is an internal mechanism that enables smooth, stable, and precise movement of the canards. This mechanism design is created to actuate the canard movement. So here at the back, we see a fairing. Basically, that's there to reduce drag. It houses a knob which is used to actuate the canard movement. And so by pushing it forward, I can make the canards point down in pitch. And by pulling it, I can make them point up in pitch. Now, the whole idea behind this mechanism is that it's more of a proof of concept for future automatic deployment mechanisms, which means that, if I throw the plane up, it'll start out with a 0-degree angle, and eventually it'll pull the canards up like that. And so it'll pull itself out of a launch and out of a dive and come back down safely. And so this design in the future would probably use springs. We'd be balancing spring forces and friction forces inside, and I'd be pushing this in to reset the mechanism, and it would automatically, the spring would push the mechanism back like that, and the canards would be actuated. So that's just a proof of concept for the mechanism design. For the actual mechanism itself, it consists of a friction lock core, a hinge, and a canard framework. And this took a lot of experimentation and iterations. While I can't show you the internal mechanism here, I will overlay some footage, and basically this design works by a friction lock module in the back, which you actuate forward and back. And basically this rod moves forward and back and moves a hinge link arm forwards and back. And this link and this hinge is made out of stainless steel. And this is a huge innovation because in previous mechanisms, for example here, we can see that the mechanism design has, the friction lock module and everything, which is basically two smaller diameter straws trying to expand, creating a lot of friction. So there's that, but this whole upper portion here is very, very large in volume. Right, it's made out of straws, and this in itself took a lot of innovation. Here we have a bearing and a hinge, and basically it's all made out of straw, and so it's very complicated, and it took a lot of time to make, and it's not as reliable because, as you can see, you can actuate this mechanism, but it has some play. It's not as stable as the stainless steel paperclip that I used in the final mechanism. Another problem with this design is that the output axle is very thick, right? It's relatively thick because it's an entire straw. By switching to a different material, we were able to reduce the volume of the mechanism considerably. And so essentially the mechanism inside is a link arm connected to a friction lock module, and this hinge is also tightly wound stainless steel wire around another wire that is the canard framework. So it's very complicated to explain, but I've included a diagram that's hand-drawn to explain kind of how it works. And so that's overall the new CSAM, control surface actuation mechanism. It's very stable, it's very precise, and it's very smooth. It's one of those things you have to kind of experience in person to really appreciate. So in addition to the CSAM control surface actuation mechanism, in the front nose of the aircraft, there is also a all-new impact dampener mechanism, which is basically, at its core, just a very simple friction lock module. Right, there's a straw there. It's cleverly integrated into the nose design, and basically, when you fly it, you leave some room here, so it struggles to get in, and then when it inevitably, touches the ground, it'll push this in, and the friction will absorb the impact. And that's just the all-new impact dampener mechanism. And there's a lot of room for future improvements here, like the incorporation of a spring internally to help with this dampening. Because I know right now sometimes when the plane flies too hard, too fast, this entire outer portion here ends up being inside, and I have to use tweezers to get them out. And so with a future iteration, I probably improve this design by using a spring or something like that. So with these two mechanisms, I was able to build a lofting structure on top of both of them, creating the side kind of profile here. So internally, this fuselage is made out of a pyramid configuration of straws in the back here, in the aft. So basically there are 3 straws on the base layer, and then there's 2 straws on top of that, and then there's one thin diameter straw as opposed to thick diameter straw that kind of just arcs all the way down forward to the nose. And so this provides a rigid and durable design, and the top smaller diameter straw provides a smooth G2 continuous spline loft. And G2 continuous is just fancy talk for continuous curvature. And so basically you can have 3 types of kind of lines, right? You can have intersecting lines, which would be G0 because they're connected. G1 would be continuous, so you can have a circle, half circle with a line. You can also have G2, which is continuous curvature, which means continuous second derivative. Basically, it means a smoother surface, right? And so this technique was, it was inspired by traditional shipbuilding techniques. On the Wikipedia page for spline lofts, you can read about the history of splines. It's used in shipbuilding. They basically took wooden beams and formed the outer mold line of the ship. And these were nautical ships. This was before airplanes. But the same principle applies here. Use straws to kind of just bend and naturally form a curve that we can loft outer panels around. This internal structure is analogous to vertebrae forming a protective frame around a central spinal cord. This outer small diameter straw kind of just wraps around the entire CSAM mechanism and also the impact dampener. It acts as kind of like, biologically a rib cage. And so basically this is the overall fuselage structure. It's efficient and results in a very purposeful design, I think. It is a significant volume reduction compared to if I used a previous generation mechanism. On the exterior here, we have the paneling of the aircraft. And so with this design, with the Astra, I took more time and consideration into paneling. Every panel was custom cut instead of being a stock rectangular sheet of cardstock. Instead, now it's several pieces of pre-cut geometries. These geometries I had to figure out through experimentation and whatnot. For example, this piece right here, right, is a panel that wraps around the notch here. And so it continues on the lower side too, but it's kind of covered here. And this is the same, gray cardstock paper that I used in some of my other planes. Basically, yeah, that's all there is to the paneling. It creates a compact and secure enclosure around all the lofting structures inside and basically the entire mechanism. And lastly, we have several integrated magnets along the aft of the aircraft. And this is to enable a seamless display stand docking. And so basically I have a stainless steel wire frame here that I made. It's probably 14 gauge wire. And essentially what you can do is just dock, right? You can just put it on your desk and use it as a display stand. And so that's another neat feature that I incorporated into this design. So we just talked about the fuselage. Now let's talk about the aerodynamic surfaces of this airplane design. Start with the wing. This wing is a tapered wing. It's pretty simple. It's quadrilateral shaped. Its planform tapers as well as its thickness. And so if you look at it from the side, taking some cues from some of my rapid prototypes, I was able to create a dihedral, and it might be kind of hard to see it here, but the thickness also tapers in addition to that. And that is also partly due to the leading edge slats, which improve stall performance. The leading edge slats incorporate a reinforcement which provides structural rigidity and also smoothens out the lower side, because initially when I created the slats were so sharp on the leading edge that when I test flew it, it kind of didn't work, because I'd guess because the flow was separating underneath because of a sharp angle, right? So if you have air coming like that, it'll separate here. And so basically with the leading edge reinforcement, I was able to smooth that out, right? And so it also provides a nice accent to the overall design, the orange, and I think it looks nice overall. Now for the canards, the design of the canards was constrained by the overall aircraft planform. And so within the main wing to nose line, so if you look at the wingtip to the nose, and if you draw a line like that, it's constrained within that line. So these canards, which are linked to the internal mechanism, is protected in case of a collision, right? If I do this, it'll be encapsulated within that triangle, and so it will never experience unexpected loads like that. Now the wing itself is more strong, and so it's more capable of handling impacts and whatnot, and so that's there to protect the canard. For the canard design, the leading and trailing edges are parallel to those of the main wings, and so the orange edges are parallel, and the trailing edge of the canard and trailing edge of the main wing are parallel. There's also a steep dihedral angle for the canards, and that is to increase stability and kind of just adds to the overall personality of the design. And the canards, like the main wing, have a leading edge reinforcement made of orange cardstock. And so this reinforcement is actually used to kind of conceal the rugged and rough and beat up gray underside layer, because the way the canards are integrated with the mechanism, there is a steel framework inside made out of paperclip, and so you can kind of see some of the indentations and remnants of the shape from the framework. And so by including a leading edge reinforcement, we kind of smooth out some of that, and it also adds a nice accent. So there's that. Vertical stabilizers are just traditional trapezoidal shaped. Basically, the left one has the Y-13A logo, as you can see here, and this was done with a pencil, and a tape layer was applied over it so it would be protected. On the other side, we have kind of the project logo with Astra and a little aircraft design inside a circle. And so this was also done using pencil, and a tape layer was applied on top. For these surfaces, I did not apply a leading edge reinforcement because they would not be experiencing structural loads that are too rough. And on the other side here, we'll see a ventral fin. The sleek OML of the aircraft meant that there's not a lot of white, kind of underside area to hold onto. And so the fin here actually serves as a handle for launches. And since it's the only structure that sticks out on the bottom, it's a load-bearing structure when the plane lands. And so it has dual internal steel reinforcements integrated into the design. It's unsightly, but it serves a function. I'm okay with that. It's not the sleekest looking fin, but it'll help with impacts and whatnot. And there's room here for future improvements too. For example, I was thinking of adding a shock absorbing ventral fin so it rotates in and out using a spring. So it's kind of spring loaded, right? So like if you impact it like this, it'll bounce in and then come back out. Another idea is a self-retracting ventral fin. The fin will retract itself into the fuselage, and basically it won't even be there to experience landing loads. But those are ideas for the future. Overall, this design, sets up some of the new processes in manufacturing and materials and design for future designs. In a future iteration, I plan on a automatic mechanism. I think that's the main goal here. So that's pretty much it for the overall design of this aircraft. And stay tuned for more, I guess.